So for our second to last unit, we're going to actually shift things quite a bit here and look at electrostatics and circuits, which really is an entire unit dedicated to the electron and the movement of electrons and what we can do with electrons. So it's going to be a pretty big change from talking about mechanics, which is what we've been talking about so far this year. Just a quick chemistry review here. I know this is stuff that you guys probably already know, but in an atom you have neutrons and you have protons located in the nucleus. The neutrons are neutral, protons are positively charged, and then kind of an orbit. Orbit's kind of a weird word for it, but we're not going to get into that technicality right now. You have electrons. The important piece is the electrons are not part of the nucleus, okay, and also that the electrons are negatively charged. All right, most of the mass, as I'm sure you remember from chemistry class, is located in that nucleus, the neutrons and the protons. The electrons have very little mass, and they're negatively charged, and they're not in the nucleus. So here we have in words what we were just talking about on the previous slide. All matter is made of positive and negative charges here. The positive charges, the protons, are located in the nucleus, and they are massive. Obviously, that's used as a relative term here, talking about subatomic particles, but protons are massive relative to electrons. The electrons, on the other hand, orbit, and again, I use quotes there, but we won't get into that technicality, and they really don't have much mass at all. We're talking about 1/1000th the mass of a proton. When we start talking about charges here, one of the things that's difficult is we live in a world that's primarily neutral. All right, because in most situations, the positive charges and the negative charges cancel out. Most objects have the same number of protons and electrons, and that means that the object as a whole is neutral, because whatever negative charge it has, that's balanced out by whatever positive charge it has. But we are going to start looking at charged objects here, and when we have charged objects, we need to know that positively charged objects are going to have more protons than electrons, and that's what gives it its positive charge, and negatively charged objects are going to have more electrons than protons. We're now going to talk about two very important concepts related to charge, and the first is conservation of charge. So, for starters, the universe as a whole is neutral. Okay, if you look across the entire universe, there's the same number of positive charges as there are negative charges. And more importantly, charge is conserved. Now, we've talked about conservation for the past 2 units with momentum, with energy. This is just another conservation law, the conservation of charge. And what that tells us is that it is impossible to create or to destroy a net charge. Okay, there will be some circumstances, and this mainly happens with nuclear reactions, but there are some circumstances where positive charges are created or destroyed. But what ends up happening is in that process, okay, the same amount of negative charge is also created or destroyed. And that means that overall there's no net change in the charge. All right. One other thing that we should point out here is that the unit for charge is the coulomb, okay, named after a gentleman that came up for the law for the force between charged objects, Coulomb's law, which we'll talk about a little bit later on. But the unit is going to be a coulomb. That's our standard. So the other concept we need to talk about is the fact that charge is quantized, okay? And what that means, I'm going to jump ahead to the definition of quantized, is quantized means that it comes in discrete units. I know you've talked about this before, possibly in your chemistry class, but it comes in discrete units. So money is a great example of something that is quantized. Money comes in units of pennies, 1 cent, okay? It's not possible to have half of a penny. All right, this amount of money that we have here written down, $31.95478, that is not possible, okay? We can have $31.95, or we can have $31.96, but we can't have any amount of money in between. It's just not something that's possible. Charge is the same way. It comes in units of E, okay? And this E here is known as the fundamental charge. And this is the charge that's on both a proton and an electron. The value of this fundamental charge is this number here, 1.6 times 10 to the negative 19th coulombs. So charge is quantized in terms of that, which means the smallest possible charge any object can have is 1.6 times 10 to the negative 19th. And then the next smallest charge would be 2 times that, 3.2 times 10 to the negative 19th coulombs. It's not possible to have a charge in between. And after that, 4.8 times 10 to the negative 19th coulombs, and 6.4 times 10 to the negative 19th coulombs, and so on. You can't have a charge in between those values. Now, with charge, it's a very, very small quantization, and so we don't really notice that there are these values in between that are not possible because it's a small amount of charge. However, charge is quantized. We're next going to talk about the interaction between charges. This is something that I know you guys know from previous classes here, but like charges, when we have both positive or both negative charges, they exert forces on each other and they will repel. When we have a positive and a negative, though, they exert forces on each other and they will attract. Okay, but I know that's something that you've talked about in previous classes. And so this is really going to be similar to how there were gravitational forces between objects with mass. Objects with charge have these electric forces between them. And as we said before, opposite charges are going to attract, like charges are going to repel. Neutral charges, and we'll talk about the reason behind this a little bit later, but neutral objects are actually attracted to any charged objects, either positive or negative. And we'll look at explaining why that happens a little bit later on. All right, so now we want to start using some of these basic concepts, what we know about charges, to explain some of the phenomenon we see related to charges. And the thing we need to keep in mind always when we're talking about this is what I have bolded and starred right here. And that is that only electrons move. Okay, protons are really the meat and potatoes of the atom. They're where all the mass is. You don't have protons transferring from one atom to another, from one object to another. That just doesn't happen. Okay, the electrons are the thing that move. The electrons are the thing that transfer, and you need to explain everything through the movement of electrons. As soon as you start saying the positive charges move, you're wrong. Okay, so keep that in mind as you're going through this entire unit. So with that in mind, let's talk about the most basic thing, is how do objects actually become charged? So how do objects become positively charged? The way that happens is by losing electrons, okay? They can't gain protons. Protons don't move. So the way something becomes positively charged is it loses electrons. How does it become negatively charged? It gains electrons. Once again, we can't do anything with the positive charges. We can't lose protons, but we can gain electrons. So we see once again that the movement of electrons is key. So 2 quick conceptual questions here applying a few of these concepts. The first is this: a piece of rabbit's fur is rubbed against a PVC pipe, which is initially neutral, as is the rabbit's fur. And the pipe now has a charge of -5 coulombs. What is the charge of the fur? And the answer here is going to be positive 5 coulombs. And our reason for this is that charge is conserved. Okay, so if they both started neutral, the way the PVC pipe became negatively charged is it gained 5 coulombs worth of electrons, and the fur therefore must have lost 5 coulombs of electrons because charge is conserved. The next one, we're going to evaluate this statement given. The positive charges went from the silk went to the glass, and that must be an incorrect statement here. And the key idea is that positive charges don't move, so it's not possible for positive charges to go from one object to another object. The last major concept we need to talk about here are the 2 different types of materials that we're going to be dealing with. All right, and to do that, we're going to look at this fairly simplified version of electrons or atoms here, and in this version we have the red central dots here for each of these atoms represents the nucleus of the atom. Surrounding that nucleus, this dark blue ring represents where the core electrons are, and those really stay with the atom. They're not really involved with bonding or any of the other interactions that the atom has with other atoms. And then you have these lighter blue, which represents the valence electrons. And that's really where bonding comes from. That's really what we're talking about with this gaining charge, losing charge business. That's all happening with the valence electrons, the outer electrons. And so we see that the core is really the same for both of these objects that we have. There's really no difference there. The key difference is in the one object, we have light blue all throughout the object. Okay? And what that is showing is that the valence electrons are just kind of floating around collectively these atoms. And we often refer to this as the sea of electrons. Okay? So this type of material that has this sea of electrons where the atoms kind of just share their valence electrons, this is known as a conductor. Okay. The other type of material that we have over here where, as you can see, the valence electrons very clearly belong to one particular atom. There is no sharing of those electrons. That's referred to as an insulator. And the key difference is really the freedom of the electrons in a conductor versus an insulator. And so here we have in words what we were just talking about. Really the key difference between these two types of materials is that electrons are free to roam around when we're dealing with a conductor, whereas electrons have much more limited movement in an insulator. They stay with their atom, with their nucleus. Okay. Typically, metals are conductors. Okay, and things like plastic and other nonmetals end up being good insulators. There is somewhat of a continuum. It's not a clear black and white where you're either a metal conductor or you're an insulator. There are some in-betweens. There are degrees of being a conductor, degrees of being an insulator. But for our purposes, we're going to kind of treat it as basically one or the other and just simplify things a little bit. All right. It should be noted, though, that insulators can still hold charges just because the electrons don't have that freedom to roam around. An insulator can still be positively or negatively charged.